Morning, everybody. I'm Charles Herring. Thanks for showing up today. That's no easy feat on a Friday morning at GrrCON, I am aware. The details that I'm going to share today can be found on my personal blog at charlesherring.com. Jot that down. Like, that was Charles Herring. I wonder what his website is. It's charlesherring.com. So this deck, the rest of the references, they're all up there. Grab them. A little bit of background on this research we've put together. Back in 2001, on the heels of 9/11, a group of sailors were detailed to the Naval Postgraduate School, and I was one of those. And we were tasked with how do we solve for protecting the networks against cyber attack from nation states, criminals, and terrorists. Not a lot going on for us in those days as far as structure around how we're supposed to accomplish that. But we were benefited by having access to great faculty. Dr. Dorothy Denning, still one of my favorite writers. Back in 1986, she wrote a paper on how we would eventually catch all this stuff, when she was at the War College, and I still think that holds up well. I was able to work with Dr. McKeechan and his partner, Dr. Copeland at Georgia Tech, on network behavioral anomaly detection. InfoWorld magazine was crazy enough to send us all of the stuff that was being made by different cybersecurity vendors at the time to test what would work, and we would send that out back when, as humans, we still tested products. And then also had the great honor to work with Chris Eagle and the School of Root on Capture the Flag at DEF CON. So it was a lot of great things going on, and like many of you, I sort of immediately fell in love with the craft of cybersecurity from that. But I remember it was one April day. I was down in the Trident Room, which was the pub on campus, still is, and I was nursing a big mug of Harp Lager in a little bit of despair, realizing I probably was not going to figure this out. This was going to be the first time in my Navy career that I wasn't going to be able to deliver on the part of the mission that was entrusted to us. And that was a little bit terrifying. We couldn't figure out what the right unit of work is. We can't do work if we can't agree on what it is. We can't roll up situational reports, sit reps to the chain of command to explain who should we go after, who's coming after us, how ready are we, what do we need in staffing, what do we need in things. We can't calculate that. So it was really uncertain, a scary time. And small group of us did what we could. We wrote some code, made some products that we used internally that moved the ball forward. And I'm really proud of the work we did there between 2001 and 2005. But in 2005, we all started going off in our own directions on different career paths. And I went into consulting, mostly with DoD and State Department, on how do we share information inside of agencies, across agencies, and engage in operations with private sector. In 2012, I was called up by Landcope, which was a company formed out of the research in Georgia Tech on network behavioral anomaly detection. And they asked me if I would do sales engineering. I had never done anything in sales, so that sounded completely terrifying. It was much more terrifying, ultimately, than I thought it would be. But one of the great things I got to do was meet with folks around the 13 states that I covered here in the central U.S. on their issues. And I saw a lot of the same problems that we were working on long ago, post 9/11. Also, in those 4 years, I got a front seat view of what does it look like? How do we raise money? How do we build software? How do we sell software? And how those things impact our capacity to solve the problems we've been chasing now for a long time. So as Landcope was acquired by Cisco, I reached back out to my Navy buddies, the folks we had met along the way, and we all met down in Atlanta to decide, should we start doing some research to see if we can solve some of these things that have been haunting us for so long. So won't get to cover all of that research. It's 9 years since that crazy day we decided to say yes, but we will get to get some of the fun parts of it. Another unique thing in my career is the network security group. In those days, our job was to figure out who should we be going after to arrest or bomb, that's attacking us. It wasn't just patch the machine, block the IOC. There was an outcome that was grander, more important than just the bleeps, blops, and wipes of machines. But if we're in the business of driving towards an outcome where deterrence is what we're trying to do, we're trying to convince the bad guys that if you mess with us, it's going to hurt really bad. If that's what we decide we're going to do, we have to treat all logs as in signals as evidence. We have to treat it with the respect that it deserves. And if you're not familiar with my crazy thoughts on deterrence and its role in cybersecurity, I wrote a piece for Dark Reading not too long ago titled "Handcuffs Over AI." And if you're scared about anything that I wrote with that word handcuffs in it, you should be. But it's a good article nonetheless. Welcome to check that out. But if we are going towards these outcomes, our analysis must be verifiable. It has to be accurate, and it needs to be explainable and understandable to audiences that include jurors of lay people. We can't throw away evidence if we're going to do that. We can't triage signals, and we can't black box do analysis. We can't take away someone's liberty, someone's property, or potentially life in national security situations because the computer said so, right? So we don't have those options. And defense attorneys have every right to question the integrity of both. How are we collecting evidence and how are we analyzing it? And because of the seriousness of those outcomes. So when we look at what does successful cybersecurity analysis look like? What would it be if we just whiteboarded it? And so the first step is just looking at the types of signals we have are in the hundreds or thousands of different formats or language types. So we need to understand what those messages are saying. Where did they come from? What are they trying to tell us about the situational awareness? In the same way that if a witness comes to a police officer and is giving testimony, the officer needs to understand why are they saying it? What are they saying? How does this possibly impact the broader picture of protection, public safety, and law enforcement? The challenge that we have is Grand Rapids PD doesn't deal with things at billions per second, right? So back when I started, we were looking at hundreds of signals per second, and now we live in a billions per second world. So we need to be able to do that comprehension at the rates of billions per second. The second thing is, how do we take those signals, tell a bigger story, put that story into a unit that we can operate on to where we know how many we have. I have 10 units to do today, or I can only do 10 and I have 20. Boss, I need help, right? Either in technology or something else. So how do we carve up that understanding into analytical units that the technical responder can operate upon? And then that final stage we're talking about is how do we bring in a broader community that understands that work product or collection of the work products and what they mean to those audiences, whether we're talking about the executives that are allocating budget, regulators, or in the case of law enforcement outcomes, jurors, judges, issuing subpoenas, and the rest. So, over the last 20-something years of me doing this, I've been as frustrated and as cynical as any of you, I promise. There are days my eyes have rolled so much that my prescription has changed 4 times since I started. But the things that I've seen in research that other folks are doing, that we've done internally, actually gives me great hope that in the next 12 months, by the time we get back here next year, not only will these things be possible, they'll be accessible broadly in the market. And I'd like to dig in a little deeper on why I have that hope. So the approach that we've been focused on is sort of what I call the Santa Claus approach, that if you could just stop time and have as much time as you needed to investigate one thing, what would we do? What would the experts do in processing that, right? And so the first step, as I was mentioning earlier, is we need to understand all of the signals, not just how to extract the IP addresses and that kind of thing, but we need to understand how does this map to a given attack framework like the MITRE attack continuum or something else. What is it telling us about the environment? And as these signals are coming in that we've understood as completely as the signals can be understood, what kind of picture do they start painting collectively? How does it fill in the gaps of who's talking to who? What's the nature of the relationships? And then once we have this picture of everything, of every computer, every user, every host, everything flowing, we start analyzing that object. And it sounds sort of crazy in cybersecurity, but we do this all the time. I woke up this morning and the first thing I did with my first cup of coffee is checked on my tune in Elder Scrolls. And that whole world is built similarly, right? There's millions of nodes and things interacting with each other in that world. And so it's a very similar approach. How can we look at our world in the way that we at least game, right? And then once we have these work units, we need to analyze them and figure out which fires are currently burning, which fires are burning hottest, and which ones do we not need to worry about because they've been taken care of something else we've already planned for in the past. And then sort of this final step is we need to bring other people into this picture. I don't know if any of you have had the pleasure of trying to brief an 80-year-old senator on what this stuff is about. It's different language, okay? And so we have to understand the audience that we need help from needs to understand our language. We can't make CISSPs and cyber experts out of everybody. It's just not feasible to do that. So we have to learn how to translate our expertise into a language that the audience can have. So let's look deeper. So I want to define a few terms. If you've ever sat in any of my talks here in GrrCON over the last decade or so, I like to make sure you understand how I'm using a word, which might not be the same way. So we can discuss that later. But there are several things that are grouped underneath the umbrella of what we're currently calling AI. And just side note, I don't think any of it's really AI, but we are calling it that. So let's talk about those words. Generative AI, as we're currently exploring it, you take an empty neural network, you have a trainer that has logic on how it's going to teach that model, and you feed it data. It's very similar. The idea is very similar to how we learn. Right now, I'm feeding you data and you're having to figure out what to do with it, right? And so it's coming in to your biological model. The great thing about generative AI, and the reason I think there is so much excitement, is we can put diverse inputs into that function and get a diverse range of outputs out of it. And that's not typically how computers have worked for us up to this point. Semantic framing is a set of natural language processing, and natural language processing is generally studied under artificial narrow intelligence or weak AI for those that are marketing against it, though I love it. I think it's the best AI. But semantic framing is really the oldest, one of the most venerable approaches from NLP. And it has very restrictive parameters. You have to teach it every language that it's learning. You can't, something that understands English and Farsi isn't going to naturally understand French. So we have to give it a lot of understanding. We have to teach it every frame, the syntax of messages, what's the etymology of those things. Graph theory we'll dig into it later, but it provides a reliable method of maintaining state over very complicated systems, whether that's me and my Templar this morning, or us looking at the people connected to this webinar remotely. There are relationships that are being formed. There are characteristics of those relationships that are changing. And graph theory provides a great way to deal with that. And as humans, we interact with that way a lot with each other. How do you know him? How do I know Mike Harris? So we deal with those things. So artificial narrow intelligence sort of covers a lot of it. But it's typically when we take a very specific piece of expertise. And so I've been to Grand Rapids now for the last 12, 13 years, many times. And I don't know why I can't make it from Pearl to here still. I still am it's one left turn, man. Like it's not that complicated. Still get every time. So I come to my expert narrow AI and say, get me to the DevOps Center. And so it gets me there. So things like that, talking to the devices that we talk to, all examples of teaching a very specific set of skills that a human would do to a computer. And normally those are coded, and both NLP and semantic framing have the benefit of being predictable and extremely fast. That's the great thing. All ANI is that way. We know how the calculation was made because we programmatically defined how it would be made, which makes it defensible in cyber conversations. Graph theory does have some struggles. We're maintaining, how do you maintain 100 million node relationships? That seems like a lot of memory, and it typically is. And how do we synchronize that across clusters? So as an industry, we're still working through some ideas on how to do that sustainably. So in GenAI, I've had a lot of great experiments, but I did find the barrier of entry to be pretty high. So I packaged what I learned the way that worked for me into a GitHub repo called Artifish. So it's just artifish.dev's the project site. They'll take you to a GitHub repo. It's licensed under Apache 2, so you can use it for research. You can build a product. You can whatever you want to do. I don't care. It's you. I hope it's helpful. I will say it's not going to work in every scenario. I'm not trying to build a toolkit that's going to work for everything for everywhere, but it did work for these things we're going to look at today. WitFoo, the company that I work for, founded. Same spirit, published the data sets. The data sets we could publish publicly, they're available on Hugging Face, and we'll look at least one of those today. And we also published a fine-tuned model to do syslog to English and syslog to JSON translation. We'll look at in a second. So those are on Hugging Face. You can find all of it on artifish.dev. So on the GenAI side, what we've been working on is started with Llama's Meta 3.1 8 billion parameter LLM model as the beginning point of where we did this. And the reason I published the data sets is many of you will choose to start somewhere else, use a small language model or whatever. So you can just use our data sets if you want to have the same outcomes on the different models. Is why I broke it out. But we started there. There's a small startup called Unsloth AI, and they've been taking these LLMs and doing quantization and other optimizations to make them cheaper to train. And for me, so right now the WitFoo model is going through 10 more epochs or 10 more laps around the data right now. That takes a week on one GPU with Unsloth. That took a month on 16 GPUs without it. So you talk about that cost difference goes from about $400 to me to about $17,000. So it's a pretty big jump. And so it's easier for me to explain one than the other to my beloved shareholders and board members. So that's why I did that. The Artifish Toolkit, I used it to build data sets. We'll look at it in a second. Used it to fine-tune the models, and there's actually a handful of different chatbot examples. I have a few more that I'll publish on retrieval augmented generation on these pieces. They'll come out shortly. Just ran out of time ahead of today. So let me give you just a quick overview of the Artifish repo. There's three major types of scripts in this repo. The first is data set creation, and so if you look at the precinct to syslog data set, this was me taking in data out of our product, out of the back end of the product, and sanitizing data and to create the data set. And ultimately, it comes down to a handful of prompts. We'll look at those in a second. That's not really that important right now. But this other one, I couldn't publish a data set on. But for any coders in here or people writing parsers or writing anything else, this is a great structure that has worked for us in a lot of use cases. But the bulk of work we do day to day at WitFoo is there's new messages. Messages are changing every day. We have to understand what those messages are to do research and write semantic frames on them. So what I did is I just took a spreadsheet, a CSV, and one column was, here's what the name of the product is. Here's a sample message from that product. Here's the code we wrote to parse that message, and here's the test we wrote to test that code. And so from putting all of that in the CSV, I was able to build some instruction sets, say, identify this message, right? And we can actually look at that data set real quick, I think I have access to it here. This is the Hugging Face. Most of this is public. You can see this one is private. And the reason it's private is, one, you don't need to write my parsers until I sucker you into coming working for me. And second, it's got our proprietary code in it. So I would not be able to do this if it did that. So essentially, there's a set of instructions. And when we're looking at training a model, for any of you that haven't done this, it's crazy easy. It's for llama-based models, you have an instruction, the thing you want the model to do. So in this case, identify the syslog message is the instruction. This is a crazy syslog message from a crazy tool. And then what the output is, what do we expect the model to respond? How do we expect the model to respond? So when we're talking about training data sets, it's really three things we're pumping into a model. There are many other things we can do with weights and other things that I'm not going to be able to talk through today, but this is the outline for how to train the model. So the cool thing for this is we can use it in our testing to say, write a new parser for this new message, and it'll generate the code. And as please read the code that comes out. I should do a whole talk on that, but it gets us close, right? It gets us the beginning of it, and then we can tweak whatever error is in there. So data set creation, part one. Next part is fine tuning. So I did these, I limited these currently to the unsloth models, the optimized models, and you can run this fine-tuned training on a gaming PC. So you don't need to go get a rig from AWS or Bedrock. So that was really important to me to make sure that whatever we're doing can be done widely and affordable. So it's just give it where is the model that you're going to start with, and there's also a download script here if you want to if you need to download one from Hugging Face or another location. Where am I going to output the newly tuned model? And then where is the CSV of training? And then the rest of this, these settings worked really well for me. And like I said, your data mileage will vary, but this got a lot out of us for just at 10 epochs or 10 laps around the data set. The model tend to learn what we wanted it to learn in that amount of training. So the bigger the data set, obviously, the longer it's going to take to train against. The data set here on this one is public. This is the larger one, which is syslog to artifact. And on syslog to artifact, we have 3 instruction sets. Create a JSON artifact from this message, identify the syslog message, and explain the syslog message. Or another way to say this is explain this in English, convert this to JSON so I can use it in higher level processing. And so and there is a workspace that's up on WitFoo called the WitQ space. Don't let me down, internet. And I was telling people when they came in earlier, there's no higher form of hubris than trying to do a live demo at a conference. So say a little prayer to the demo gods. But let's say we want to just explain it in English and extract a message, and I'll pick on a VPC flow log that I put in my clipboard. So unless you do this all day, that just looks like a bunch of random confusing things, but this is how computers talk to each other. They talk in a way that the other computer doesn't understand, that the human reading it doesn't understand, but I digress. Do that in a therapy session at lunch for anyone who wants to join that. So that didn't do what I wanted to do. Try again, saying LLMs, but okay, so it gives me an explanation of the client IP, the source IP, the destination IP, and it explains that message in English. If we wanted to do the same thing, but do an extraction of all the fields to a JSON structure, oh, come on, GrrCON. All right, someone's messing with my thing. All right, get you guys, I'm going home. Do it on my private one that you can't, oh, it's not even started. Man, stupid Charles. All right, so anyway, that's that. So you can train the model. I do have the chat bot, so that space, if you want to do any of the spinning up of the chat bots in different configurations, those are also in that space. So cool to be able to translate syslog into a structured JSON object so that we can use that for future processing, just understanding it. If you're like, what in the world could this be? It's a good starting spot. And I don't have it enabled on that workspace, but there's a great library called OLLAMA, which is online llama, and it essentially will do retrieval augmented generation on that model to do an internet search to bring in any additional information that may help it, which is what we would do as analysts. Like, what is this message? Help me out, Google, or whatever your flavor of search is. All right, talk about that. So the downside of that is, one, reliability. But the second thing is you can't wait 6 seconds to process a message if we're getting a billion of them a second. Elon Musk can't afford the GPUs to do that. So it's cool. It's helpful. It helps us in generating new parsers. But, with the current state of technology, I say, GenAI, the amount of tokens we're doing is like having a 2400 baud modem in a 10 gigabyte world or 10 gigabit world. It's not fast enough. But what has worked in our research is the semantic framing. So using generative AI to build a frame, and basically, if you think about the way it works, is you take the variable information in a message. So you identify that's an IPv4 address, replace the actual address with a variable that says IPv4, do the same thing for timestamps and integers and all those things, you're left with a fingerprint that explains where things fit into it, sort of a template. And so we use a no collision model, so that there's no collision on the fingerprints. A fingerprint always matches or it doesn't. And if you have a match, then you can put all of the things you know about that message. That IP address is a client IP address. This message was written by Tom Cross back when he was at ISS. You can write the etymology of that message. This fires when it's related to privilege escalation, right? You can put all of that on this sort of notebook that we call a semantic frame around this message. So not only do we know what things are in it, we know why those things are there. And so it's essentially just a highly evolved type of parser, but it can run at billions of transactions per second. It does run at billions of transactions per second all over the world in all kinds of use cases. From a forensics perspective, when we need to get in front of a jury or a great defense attorney, you can explain exactly, you'll put them to sleep, but you can explain how we parse that message and came to that conclusion with certainty, which I couldn't do on the output of an LLM text generation model. The downside is it takes a lot of research. We spend sometimes several hours to a couple of days researching different messages. And at some point, I'll be brave enough to write the top 10 worst message formats, because I do have a lot of anger that needs to come out at some point for what were you thinking, buddy? And many of you I know would definitely give me a like and on that subreddit. But GenAI has helped us. We have a whole pipeline to where if we don't know what a message is, it goes into pipeline, it makes a guess, starts the developer somewhere better than good luck, right? And so it is reducing our time in building parsers. We're still sort of working through that, but it is a great help there. So bless you. So when we combine all that together, we can push really fast, highly accurate, defensible, basically signatures down to pipelines that process this. The output then is a JSON structure with everything in it, explaining everything about this message, preserving the original message, doing as much non-repudiation and chain of custody tracking as we can in that message. JSON, great compression, hash is great. Apparently the internet runs on it or something. So it's a great format for storing all of that. In a case where we don't know, where the system says don't know, which is if you've been in cybersecurity, having a team member that doesn't know how to say I don't know is the biggest vulnerability to patch. But the system says, I don't know, ships that tokenized version of the message up. You're able to then shoot some tokens into it, do the research, build the parser, push it down, do forward-looking, retrospective understanding of the messages so that you are able to maintain that full comprehension in that pipeline. And again, as I mentioned, you can shrink that down with whether that's Copilot or a RAG-enabled GitHub Copilot or whatever your LLM of choice is. We talk about Kevin Bacon a lot at WitFoo, but when we talk about graph theory, analysis of all types, no matter what we're trying to put together, does require us to understand these signals. And as we talked about, that's daunting enough. But we have to use those signals to draw a bigger picture. We've been in signal analysis for so long that it's hard for us to get out of it. But signals are just a whisper of a much broader story. And so we have to organize how the different signals relate to one another in a broader story. And graph theory implements that very human thing well in computers. And so as every signal flows in, the picture becomes much, much clearer. And it's one of the reasons I'm so adamant about the dangers of triaging signals is we wouldn't ask a homicide detective to choose between, do you want ballistics, the medical examiner's report, or witness testimony? That would be horrible for everybody involved. Well, except the criminal. They'll probably help the criminal out, so I might admit that. But and in this, some signals will temporarily create noise, right? but then you'll have an augmenting signal that will explain the noise later. And so just as, anybody judging anything, any investigator is benefited by having as much fact as possible, as long as the processing time, the comprehension time of that evidence isn't overly cumbersome. And also we can explain it in court. How do you know that this machine is related to this machine? How do you know the characteristics for this? So it's highly defensible. So for those of us old enough to know what Schoolhouse Rock is, let me show you how a graph is made. So we'll take an extracted signal. This is some components, some attributes of a DHCP lease renewal. Normally not something in the SOC we care all that much about in itself, but it's telling us that client A exists. Its current IP address ends in .43. We have its link layer, its MAC address. So we know it exists. We're tracking state, client A is there, and we know a little bit about it. Then we receive a second signal that tells us from a different tool, this case from CrowdStrike Falcon, if it's, I'll save that. From CrowdStrike Falcon, that tells us that user one's logged in and file Z is present and the user is interacting with it on the computer. So now we have what we call 3 graph nodes and 2 edges relationships, and you potentially could draw a relationship between the user and the file here, and that would be defensible. Receive a third signal that tells us that the IP address belonging to client A just communicated with a FQDN called server B. So now we have a 4th node, and we're tracking state on that. And then beyond understanding in this graph that there are relationships, and that's the first thing. What are the relationships? The second thing that's even more important is what are the nature or the characteristics of those relationships? So that second signal told us malware, right? This machine's exploited. This is, or potentially exploited at least. So instead of focusing on the signal, we can inherit that implication into the relationship, that the relationship between user one, file Z, and client A is potentially indicated in whatever kill chains, whatever progressions of crime theory deal with exploit. And then Cisco Firepower told us there's a botnet connection between client A and server B. So we're looking at the relationships. And of course, this is happening not at a few connections and hosts, but across millions of different relationships. And many relationships will be as benign as you would expect, right? So when we look at, okay, what signals are important? The question to ask is when do we use what type of evidence to do what type of investigation? So, as defenders, we don't get to choose how we're going to be attacked. We don't know if it is going to be ransomware. We don't know if extortion be ransomware or data theft. So we have to proactively start collecting evidence. And unlike physical law enforcement, we don't get to go back and get fingerprints later, right? We either know to collect the evidence before the thing exists or it immediately vaporizes off the wire. In this example chart, I took a handful of things that I used in a briefing to Gartner some time ago on what things do you have to have any hope of catching a different type of crime threat. What things tell a better story and what things are helpful. And where you have gaps in evidence, it means expensive work that I may need to do forensics or something else. So, and this is just a small sample. And if you think through, if you do a table exercise on what evidence will we need if we did an investigation for ransomware or insider threat or a SCADA attack, whatever the things are that could be vulnerable to, what damage could occur, you're left with something looking like this, which doesn't leave a whole lot of things for us to say we can just send a dev null. So if we look at this almost fictional story, I just want to use this one to look at how triaging signals can impact the outcome graph. So this is a data theft. And so on the left, we have a machine that's become compromised, is ultimately scanning the network. The machine's on the bottom left. Is able to compromise some credentials, use that to pivot into the network, stage some data, stage it to the DMZ, get it out of the network, drop some malware, have persistence, right? So this tells a story, and for most of us that have been doing this for a while, we would, if we understood what the what the graph's saying, we get this how this is data theft. So it's fully constructed. It's made up of telemetry coming from network defense devices, coming from things defending against identity attack, data loss protection, or network flow is in there, and endpoint defense. So if we just say, let's just take away endpoint defense, let's just take away our EDR or whatever we're using on the endpoint, the graph doesn't change too much. We're not too badly degraded. We can still see data thefts happening, that it's moving across the network, that it's leaving the network. We just don't know that there's malware dangling on DMZ01, but I don't think most of us would close up the day without going out and sort of either doing a deep dive on DMZ1 or restoring it or reimaging it. If we put endpoint defense back in there and take away identity, we can still see data theft. We can still see there's a couple of infected machines. And we can see lateral movement of data through the network. But what we lose in this case are two things. One, we can't see how the data moved. What was the method of moving the data? And we also are unaware of credentials that are still compromised that we need to interact with to reset them so they're not continued to use in a persistence campaign. So if we restore identity and just take away DLP or flow, just monitoring how machines are talking to each other, this is now more of a puzzle than it is of a help. We would see, okay, I've got a machine that's infected by the artifacts telling me there's malware on it. That's a no-brainer. I have a command and control socket on another machine, and then there's credentials that are between them that are probably compromised. But we have no idea at this point, from this information we've collected, the data's even been stolen. We'd have infections we're dealing with instead of dealing with the critical, potentially catastrophic issue of data left our network and what the characteristic of that data is. So we'll wipe the two machines, we'll reset a credential, but won't be able to do the things that are most needful in criminal investigation and an incident response. If we take away the identity, take away network communications and take away identity, we're left with two machines are infected. And so we wipe the two machines, we go about to the next, and these would be 2 units of work too, instead of one. We wouldn't even know they have any relation to one another and move on. So short of that is, the more data we pull in, the more that data informs what the other data means, the clearer the picture is of what we get when we're informing a graph. The second piece we look at is narrow AI or artificial narrow intelligence. Building the graphs are pretty easy, from a programmatic point of view, but analyzing the graphs can't be done without programmatic assistance, without computed assistance. So we can't go in and say, oh, that looks interesting, let's add this to the graph and let's go through it. We have to inspect everything all the time, which means we need to build some algorithms to do that. So narrow AI is pretty cool in that effect that we can say, what would an expert do? So if we look at, weather forecast or, GPS navigation, those are great examples of narrow AI or weak expert models. But they do take a lot of time to research, getting folks like us into a room and say, what would you do in this investigation? What would you be looking for? What queries would you run against the data? What actions would you take? What enrichments would you look for? And so the first thing is just sort of understanding what does the wit of the broader audience say? What are our skills? How would we apply that and understanding that? And that's a lot, just understanding what the best practice to do. And then we have to teach a computer to do those things. But querying a graph is pretty easy. We can look at the graph. Let's see, what is my next slide? Okay, yeah. So when we're looking at and using that from a cybersecurity perspective, we can build a model to say, look at the characteristics of data moving around the network. Is it too much data? Is it anomalous data? Is it suspicious? Are there behaviors that map to something like the MITRE attack? And that should be an at, not an at, but to the attack continuum. And so we can see this relationship's indicating data staging or privilege escalation or exploit or persistence or botnet. And so we're just looking at the relationships and say, okay, now that we can see those things, how could they fit together? We can also look at corroboration. If we have multiple tools telling us that a machine is baked, we have higher confidence that it's baked, right? And so that corroboration of tools is important, and also how we typically do law enforcement. We can look at the old school things like, what's the most alarming host? Which one has the most alarms or the most alarming alarms? And then from that, we can teach ANI to say, let's have a theory of a crime. Let's look for what it would look like on this whole graph if someone was trying to extort money via ransomware. Let's look for what data theft would look like. Let's look for phishing attacks on the graph, and then have it pluck out of that the information around a unit of work to put in front of a human. And so that's sort of the next step there. So in talking to Detective Bill Rich out at LAPD, in the early research of this, he explained that when he rolls up to a murder investigation or any investigation and he sees 20 bullets in the house and 20 shell casings on the ground, the first thing he does is draw a big circle around all that in his brain and starts posing theories of crime. He's like, okay, it's probably not a bank robbery. There's no bank, right? But it could be a drive-by shooting. And so he starts going after evidence that informs, that either proves that theory or disproves that theory. And so we can do the same thing on observations. Does the evidence that's flowing into this unit and flowing into the graph support our theory of crime? And so the more support we get, the more it moves towards certainty, or one in our case. And the more the evidence disproves it, it pushes to zero. And so you might have multiple theories running at the same time. Is this a data backup, or is this data theft? Is this is this phishing, or is this training, right? And so is this the red team gone amok, right? So you can have all these theories on the same unit, have different units that have different theories. And again, where no triage models are important, where we're taking in all signals, is every signal, and it sometimes can seem benign. It can be something like a DHCP lease renewal can tell you that machine's not there. Or when we look at things like magic carpet attacks, where how's that user in two different places, all of those signals collectively can paint a broader picture, is why it's very important not to triage on that. And so, all of that we've looked at to this point is available in varying degrees commercially. But, I've been doing this for 20 something years now. And I love the tools my team has made, but unless you have deep cybersecurity knowledge and WitFoo chops, this just looks like nerd art. And so how do we translate something very technical to potentially a juror that's day job is landscaping, right? And his fate, is connected there. And so this part's really exciting to me, because we've sort of been stuck in these small us's, right? We have these small groups and siloed off from the rest of the business. So if we can explain intelligently and accurately what's going on to other people, we can recruit them to help us, whether that's for law enforcement, getting budget, getting training, and those kind of things. So the research working on now this is where I think generative AI is very, LLM is very powerful, is how can we translate structured JSON, a collection of evidence and graphs and nodes, how can we translate that into English? And it's pretty simple, right? Computers understand the structured stuff. You give it the English, and what it ends up looking like to get that last mile is basically building a data set like we were looking at before, where the instruction is explain this craziness. The input is the work product that you've created, the JSON structure with all of the evidence in the format that you're working with. And the output is how you would explain it to a human. And so starting to work with some of our education partners on building. So I've created synthesized incidents, because I can't use live ones because, privacy. And but we're starting to build these different explanations out, and it doesn't have to be explain it period. It could be explain it to someone, explain it to an executive, explain it to a legislator, explain it to a U.S. attorney. And so building these data sets out, that's the only thing that we're left with, is building them and then training the models. The models understand the structured JSON, the structured information so well that if we can give it the explanation, it can map to say, okay, I see where you got that piece of information in the English from that piece of information in the JSON. And obviously we can do it with much more than English, not to bias this just for English speakers. But that's very exciting to me on that last mile, because we are really close. It's just building data sets. That's work. We don't have to solve something big to make that part work, to get it at least close. And of course, whenever we have that, we do want humans making sure my computers can't go to prison. They don't care. They're already in jail. So we can't punish them for doing bad. So that's on us. So we sort of have to watch them. We don't know what they're going to do. That's a terrifying part of this phase in history. So just wrapping things up, NLP is proven to be a solid method for fully comprehending messages at the billions per second rate. Generative AI is got a lot of potential in helping us maintaining, whether it's parsers or semantic frames, to do that work at rate. Translating JSON structured signals onto a graph and maintaining state on everything is a fantastic way to get out of signal-based or host-based analysis and get into looking at the whole world and how things put together. And building narrow AI models to inspect that graph, to build units of work, and potentially, this is the crazy thing, they can create a unit of work, analyze a unit of work, and in many cases, close out the unit of work. Some of the early research we were doing at the University of Chicago, we just watched their SOC. And most of the investigations ended with, oh, this got quarantined by endpoint, or this was stopped by network defenses, or identity shut this down. And like, okay, how do you know it shut it down? And so you can teach that, and as we've been able to do, into the ANI, and say, when it says it stopped it, check to verify that the evidence supports that it stopped it. You don't delete the work unit, you keep the work unit, but you take it out of the queue as a burning fire, mark it as a disrupted, stopped fire, and let the human analyst, focus on the fires that are still burning. And then generative AI in the last part of this is really encouraging on how can we better express ourselves, express our work units, whether it's the single work unit, or we had 3,000 data attack boss, we need help. We can't do this many work units. We need more people, or we need tools that are going to deal with this, and making business conversations that even the suits can understand is a really important part. So I'm coming up on time, so out of respect to you guys and the next speaker, I'm not going to take any questions up here. I do want to hear your questions. I want to hear your stories. I want to hear what you're working on. So, hit me up. All my social stuff is on charlesherring.com. You can email me at charles@witfoo.com. If you do hit me up on social media, please just put GrrCON or something like GrrCON so that I don't shunt you to death null. I got a lot of people pinging me for stuff I don't care about. Details on the open source stuff is on artifish.dev, and the crew at the Impellix booth is they've got the duty of chaperoning me this GrrCON.